Sorry. Got it. There we go. Okay. Got it. All right. And the sort of main sort of context for our work is something I'll kind of refer to as a conjecture. Which I'll kind of attribute to Cohen, Lenstra, also kind of Cohen and Martinet. Consequence of their sort of heuristics or philosophy for the behavior of class groups. But in sort of a loose term, what it wants to assert is that for any group G, any good prime L, sort of a limit they might refer to as, say, the average over K in F of G of sort of the class group of K, L-torsion subgroup order, which we'll define sort of to be equal to the limit x goes to infinity, 1 over the size of the family, x, sum over A and F G of x, of this quantity. Let's assert that this limit exists. So really sort of Cohen and Lenstra and Cohen and Martinet kind of predict quite a bit more. They're sort of often quite a bit more specific, also going to with this prediction. Really sort of their assertion, I think, in my mind, is that there should be some sort of probability distribution on the space of finite abelian groups or finite abelian L groups from which you can kind of deduce things like this. But any questions sort of about notation or setup like this? All right. So there's not very much known towards sort of this conjecture, even this kind of crude form that I stated it here. So in cases, well, you can look at G being the symmetric group on 2 letters, and L being the prime complete. In which case, if K is Q, this is due to Davenport and L1. '70s. And if K is any global field, this is due to Daskowski interval. And this work of Daskowski interval is actually going to be quite important for this talk today. And other sort of cases include also, or sort of are limited to work essentially of Bargava, with sort of G being S3, L equals 2, where again, if K is Q, Bargava is kind of a consequence of this kind of quartic fields. And in the global case, this follows from work of Bargava and Wong. These are essentially sort of the only known cases, or at least sort of only previously known cases. And the result I want to tell you about today kind of adds to this list. In the following form. If G is a 2 group with the transposition. So just again as a reminder, all of my groups are permutation groups. So I sort of can talk about whether or not they have a transposition. Then sort of the average exists. I should say for L equals 3. Okay, so I think a few remarks are in order. So I think the first thing to highlight is maybe sort of the first interesting example of this. So what do you need to have it be a 2 group with a transposition? Well, sort of the simplest new example is G being the dihedral group of order 8, sort of acting on 4 letters. And if K is Q, this average works out to be about 1.42. So we kind of be very explicit about kind of what these averages are. We sort of tell you exactly what they are. They're given by some sort of infinite series in this for this theorem, but it's something you kind of compute to arbitrary precision.
Is this theorem for number fields or global fields?
This is for number fields. So here, number field. I expect it probably will work also for global function fields, but I don't want to kind of go out on a limb and assert that definitively. I can kind of imagine some things being a little bit different. Yeah.
Is the average the expected average?
Aha, that's a great question. So I think, so the reason why I actually stated the Cohen Lenstra Martinet kind of heuristics in a kind of loose form like this is I think they wouldn't actually be making concrete predictions about this particular sort of class group average when ordered by discriminant. Okay, so in particular, it's not going to be equal to kind of the right number, but I'll give you the right number in a little bit. Other questions?
What is a transposition?
Great. A transposition is in a permutation group, something that just swaps 2 elements. And I think sort of the next remarks I want to make are going to have to do with sort of this hypothesis. So I think this hypothesis is maybe the one that's like the weirdest to process. Other questions about the statement of the theorem beyond sort of the transposition?
Well, someone should ask if you have the average converging power savings rate, maybe.
That's a great question. The way we prove it, we give it purely a soft asymptotic. The method could sort of extract a power savings. We'll kind of highlight exactly what we needed to do that. It's nothing sort of fundamentally new or interesting.
And you also have the asymptotic for the size of FG of X itself or something.
Aha, okay, great. So maybe I'll sort of write this point. That's going to kind of tie directly kind of into what I want to say about transpositions. So if G is a 2 group with a transposition, and then it's known that the size of this family grows like some constant times x. Some constant x. Some constant c. Of course, depending on G and K, I guess G and K. And if G is a 2 group without the transposition, then we don't sort of know definitively the size of the family in every case. But what we do know is that there are many fewer such fields. So in particular, the number of G extensions is divided by big O of x to 1/2 plus x. So the first thing to kind of remark on then, with regards to this hypothesis on the transposition, is that these are kind of the groups that you should expect to be kind of generic amongst sort of Galois groups of fields with 2 groups sort of as their Galois. Right? Sort of if you don't have that, you're kind of in a much thinner family of fields. You kind of shouldn't expect those to be sort of as easily accessed.
And you could say who those estimates are due
Sure.
to. I mean, or even just out loud.
Yeah. So the first one kind of follows from combining a lot of different results. So I think sort of the most important work when we do the work of, I guess, Kluners and Mala on upper bounds for Mala's conjecture for nilpotent extensions, and work of Kluners who kind of have certain Reed product Galois groups. That turns out to be enough here. And this, I think, would follow from Kluners and Mala. Okay, so
What are you guys the ones that put it together to get these statements?
we are, but I sort of don't want to claim there's any novelty. All right. So again, so this sort of hypothesis about a transposition shows up in sort of saying that, again, like these are the kind of generic Galois groups that are going to appear as two groups. But it's also going to end up being important in our proof kind of in a very structural sort of way. And to hit at that, and also come back to this question about kind of nice numbers or kind of correct averages. If G is a two group with transposition, then any extension in FG has a unique index to subfield F. So any two group, or sort of any field whose Galois group is a two group, will have at least one index to subfield. And it's sort of the transposition buys you that that subfield is unique. And one thing you can do is you can also ask about the relative class group of K over this extension. Sort of then sort of the same methods. Yield sort of the following, that if one restricts to fields A in FG such that the relative unit rank is some specified number, so such that the rank of the units subtracting sort of the rank of the units of OF is some fixed number U. Then the average over K in FG, this family of relative class group, p-torsion, is a nice number 1 plus 3 to the minus U. And what's more, this is sort of as predicted. By Cohen. So I'm going to punt a little bit on the definition of a relative class group, but I'll say, I'm going to write down kind of the expected sort of thing there.
Can I ask you a question?
Absolutely.
About the statement about the unique index to subfield. So maybe I'm missing something, but are you saying that G has a unique subgroup index too?
Not quite. So sort of here, what I'm kind of basically saying to do is, so for example, I kind of sort of imagining fixing the signature of K and its subfield F. And so kind of the signature of K alone is not enough to determine the signature of its subfield F. All right, if I have, say, a totally complex D4 quartic, it could come from a lot of different things. Sort of its quadratic subfield could either be real or imaginary. But I want to kind of imagine fixing kind of all of that and saying, let's only look at the extensions for which that kind of relative unit rank, which depends on that the pair of signatures, is my favorite number U.
Sorry, I'm bit- this,
Yeah, because in your statement you say then any extension has a unique index to subfield. The upper board. Yeah.
Yeah.
Over there you yeah. So
Yes. So by index to subfield here, I mean that K is a quadratic extension of F.
And is K the Galois closure or the degree n?
K is the degree n dot.
okay. Yeah, okay.
Any other clarifying questions?
I think you suggested this, but you can further restrict to the, you can further just restrict the fields to give a signature and do that average.
Yeah, so there's one sort of like sneaky sort of thing here, which is we don't strictly speaking know that all possible signatures occur.
Okay.
And so if we sort of assert that such signatures do occur, then absolutely yes. Any other questions? And I sort of think I owe you kind of a definition or way to process the relative class group. And in particular, it's sort of what you would expect it to be. So where well, but what's important to know right now is that this sort of order of this relative class group is just exactly equal the order of the three part of the class group of K divided by the order of the three part of the class group. And so we sort of see a hint also kind of how we're going to end up approaching this theorem and what the strategy of the proof is going to be by virtue of this sort of index to sum. This is going to be kind of really kind of a key player. It's going to be exploiting the quadratic extension K over F kind of throughout. That's going to be kind of the main focus of things. So what I want to do is I want to start talking about kind of the strategy of the proof and kind of getting into that a little bit. Any other questions before I do that? All right. So what is this strategy going to be? If you have this index 2 subfield sort of around, you should try to exploit it. And in particular, the basic strategy of the proof is going to be to proceed by induction. Exploiting the extension so in particular, like if you sort of understand kind of the structure of these sort of extensions with the all group and 2 group, there's a very natural kind of first step in this group, which is basically, so in particular, if I want to try to study the sum over G extensions K of this 3 part of the class group, which again, because I understand sort of the hidden denominator in this theorem by sort of virtue of this board, so sort of essentially what our theorem wants to study is I can take this and I can break it up based on sort of this subfield F. And also exploiting this factorization just kind of in reverse. So in particular, I can make this a summation over F in some family of extensions, which I guess we'll denote H here, kind of write H in a second, of the 3 part of the class group of F, and then a sum over these G extensions K, for which this index U subfield of K is this sort of particular sort of field F. Where H is kind of the generic Galois sort of root of such a field, which turns out to be kind of well determined from H or from G. Okay, and one sort of final thing that this transposition hypothesis buys us is we look at these extensions. These are all quadratic extensions of F, and this transposition hypothesis says not only are they quadratic extensions of F, they're kind of actually what you should expect to see is kind of the generic Galois group over your base field of such a quadratic extension. And so in particular, I want to say that this is approximately equal to the same sum over F and FH of this 3-part of F times now sum over all quadratic extensions of F with discriminant at most X of this 3-part of K over F. So this approximately equals is a little bit of a lie, of course. And there's certainly some work needed to make it kind of fully justified. And actually, so sort of interesting that I'm happy to talk about it maybe in the questions part of this talk. But what this then basically says is, well, we should try to go over these sort of fields F, think about kind of this average, and just try to add it up. And that is ultimately what our main term is going to be. But the difficulty here is, well, we do know how to estimate this thing asymptotically in X for a fixed field F. This is exactly what Datzkowski and Wright tell us how to do. Which conveniently I have here, but I'll kind of say again. Handles with the inner sum. But their result is actually a soft asymptotic as well. And what's more, it kind of like is not maybe inherently soft, but it's clear that it's kind of going to depend quite greatly sort of on the size of this field F.
The problem is the Adela is too quick.
I'd sort of love to hear more, yeah.
Follow them.
All right.
And the thing about Adelas is they smooth out very quickly there. That's actually where they ran into trouble with reform, right? What's the guy's name?
Yeah.
So now you're going to show us how you can handle this quantitative.
I am to an extent. I mean, I'm going to be kind of appealing to some of Datzkowski and Wright's work, so we'll kind of, I'll finally sort of hear more kind of at the end, maybe. But so again, they sort of handle the inner sum, provided that F is kind of very small. So again, you can kind of, if you're willing to kind of work hard enough with what Datzkowski and Wright do, kind of incorporate recent advances due to people like Margaret Schenkard Zimmerman, sort of also particular kind of Thorne and Hanaguchi, you'd be able to kind of make explicit what very small means. But at any rate, it's going to always mean something very small. And so
In terms of X,
F is very small. Yeah, I suppose in terms of X, I'm usually going to think about kind of X as a range of discriminative F, but yeah. And so our main goal, kind of our main technical result, is going to give a way of kind of bypassing this and not needing to care what kind of very small actually means. So the main technical result is the following, that if I sort of take this same summation at this
first guy I've seen ever wrote some backwards like that. You start at the bottom. Go to the top.
Yeah, well, great. I confess I sort of like doing math from the bottom up anyway, so it kind of fits my character. All right. So again, I'm going to write down exactly the same sum first, and then I will modify it in just a second. This is exactly the same summation that I wrote over there. And the one extra thing I want to add on here is the condition that the discriminative f is bigger than some parameter y. And what I want to then tell you is that this whole quantity is big O epsilon of x over y 1s.
That gives you a uniformity in the size.
That's exactly right. So in particular, what's sort of important to extract from this is that this I've written here exactly the correct power of x. We sort of want. We want x to the 1. I'm not writing on x to the 1 plus epsilon. The epsilon is instead in the y, where it's kind of innocuous. And in particular, this sort of technical result lets us assume that this field f is as small as we like. We can kind of then just formally kind of apply Descartesian right and add everything up.
For the power saving.
Yeah, of course. For the power saving, you have to kind of make explicit what very small is.
You would need a small power.
That's exactly right. And the technology absolutely exists. It's just would be a little bit kind of sort of painful kind of carry out kind of in this work.
You can take y equal 1 here.
You can absolutely take y equals 1. So in particular, this technical result implies that the limit soup is valid. Great. Other questions kind of about sort of this technical result.
Actually, you take the inner sum asymptotic.
Yes.
What is the rough dependence on discriminant f on the in truth?
So the sort of like the kind of main term, in other words, mild, like discriminant to the epsilon. You're sort of going to see like a residue.
Sorry, to decay with the discriminant.
Oh, I see. I understand.
Well, the length of the sum decays.
So it's like
Yes.
x divided by the discriminant.
Yeah, it's sort of right. So if I kind of, after accounting for conductor discriminant, which I might actually do sort of right now, basically sort of the summation is of length over sort of product extension of f with relative discriminant divided by x over this guy squared. So in that case, sort of the truth is sort of 1 over dis squared. And kind of that's where you see this sort of y to the 1 minus x. So let me just actually write that explicitly. So for a conductor discriminant, what we sort of know is that sort of disk F is no bigger than x to 1/2, and the relative discriminant p over f is no bigger than x over disk F squared.
It's like a square-free sum.
Very much, yeah. All right. And so this parameter is one that I don't strictly need to give another name to, but I find it convenient to call this little x as kind of a bound on the relative discriminant of the extensions in question. And my little x's are distinguished by kind of the extra series sort of on either. All right. And so how are we going to approach this problem? Trying to sort of adding up sort of these class group extensions or class groups. Well, it turns out that class group elements or elements of the relative class group correspond to S3 cubic extensions of so here, sort of the actual definition of the relative class group is important. I'm kind of thinking of this as the things that are in the kernel of the norm map from class group K to class group F. But it's just kind of a generalization of sort of the standard result over Q. And so then what this does is it gives a kind of transformed problem. Where instead of kind of studying just class group elements, I can try to study cubic extensions. So given F of bound, the number of relative cubic extensions all over F, this all over F up to this little x bound, which again, I don't strictly speaking need to define, but I could have mentally remember always x over df squared. But any x greater than or equal to 1 uniformly in F. So in other words, I want to get a bound on the number of these relative cubic extensions that holds for any x greater than or equal to 1. Coming back to Paul's question, it's sort of very key kind of here to have that kind of uniformity, and where we know exactly how it depends on this field F. All right. And in particular, we sort of have kind of the kind of main, maybe sort of the key sort of proposition. Is exactly such a bound that kind of does sort of makes clear exactly how we kind of assemble these ingredients. So in particular, what we show is that for any x greater than 1, whenever these cubic extensions this is bounded in terms of epsilon as this epsilon times x. And if you sort of look at this, I kind of think this should give you about like a 1 plus epsilon loss over kind of the expected truth, which is this x over dx squared kind of thing, which actually falls just a little short of being something like this. And so what we actually do is this is a result we get kind of pointwise on field F. And this may be improved to big O of Pisca to 1 minus delta plus epsilon times x kind of on average over f. And okay, if you actually sort of check the numerology again, it's not going to quite line up, but I'll explain kind of where that kind of gap is in this. This is kind of what's necessary to get this sort of kind of result to hold plausibly. So questions kind of about what this is saying. Now I want to kind of tell you about kind of like the steps involved in this sort of proposition.
I understand what you meant when you said the numerology didn't line up.
Aha, yes. So if you actually take this result, kind of plug this in kind of way up here, you'll actually get, I think the way I set this up is you get a 1 replaced with a delta. That's perfectly good for us. We could get away with that, but the proof will actually give a 1 minus epsilon at the end of the day.
Percent average with respect to F, is F, how big is F?
F is just any field.
That is on average over.
On average over F. I'll kind of make clear kind of what I mean there, but
And maybe for your technical result, will you eventually take y to be bounded by x to the epsilon? Will you apply it?
it would imply y is x to the epsilon. I'm actually just taking it very, very small. I'm kind of like basically letting it just kind of tend to infinity formally. But I think in practice, one could and probably should take the some small power of x, but that would kind of again require certain other things to be made explicit that haven't been yet. All right. So what are kind of the steps in the proof of what I'm calling this kind of key proposition? Well, I guess sort of one remark I kind of wanted to make sort of about this result is one thing I sort of like about this is in many ways this is kind of an analogy with sort of the problem of kind of bounding torsion subgroups of class groups itself. So if you were to ask this question where L over F is an abelian cubic extension, by sort of using some class field theory, you'd basically sort of reduce this problem to what kind of bound you put on the 3 torsion subgroup of the class. So this is kind of a non-abelian analog in that sense. We're sort of asking what is basically the best power you can put sort of discriminant here that gives you kind of the right exponent of x.
Yeah.
Okay.
Yeah. Thank you very much.
So what are the steps in the proof? Well, the first thing you should do is you should just kind of see what you can get with bare points. So particularly you should kind of undo this translation we made to cubic extensions. You should go back to class groups and just kind of see what that tells you. Undo translation from class groups. And just sort of use sort of a bound on the relative class group. So in particular, we will use sort of the best bound available to us in general, which is the trivial bound. So the trivial bound of the class group is that this may be bounded by discriminant of f plus epsilon times So this is kind of a relative of sort of the trivial bound on the standard class group, but it's kind of accounting for the fact that we're looking for relative. What would this give you? Well, for this cubic extensions problem, it gives bound in the form this f 1/2 plus epsilon minus x 3 times, which is sort of far from enough, but it's at least a start. And I'll just say, if you're kind of trying to pay attention more to sort of the numerology of what is presently this board, I'll say kind of handles fields F with disk F. A little bit more than x to 1/3. And I guess I should say also that this is useful if x divided by this. All right, so that's kind of the bare hand sort of approach. This is what we get at first. What's the next thing we should try? Well, the next thing we should try is using some of the technology available that sort of gives us the asymptotic and see what that gives us. And maybe Peter has some ideas on how to improve this, but kind of the second step is use the Shintani zeta function. As developed by Transposition, right?
Double gamma function, which is frightening.
Yeah, there's a lot that sort of was kind of a little bit difficult to extract from their work.
Because if you want to shift the contour count, you need to get control in the critical strip, and a double gamma function means worse growth. And I'm sure you know how to deal with that. Anyway, you don't care what you get because of that very strong patch unit.
Exactly right.
You really saying you can do one at a time.
Yeah, so more or less like so kind of a lot of kind of the particular analytic issues of the Shintani zeta function are handled because we're going for an upper bound. We can just like smooth the crap out of everything. But yeah, that's right. I think like if you wanted to try to extract a true asymptotic from this, again, quite a bit more work would be. But in particular, I'll say that this kind of works. It's large, which for an upper bound purposes is actually fairly easy to sort of make explicit. And if it'll work if x is bigger than, let's say, this f cubed. And in particular, this will give a bound that is essentially perfect. This parameter levels. So again, you can lose the disk to the epsilon, but again, you have exactly the right power bounds. And so if you don't know sort of what the Shintani zeta function is, it doesn't matter so much. I'll just say that it's kind of a lot like a degree 4 L function over F, except that it has a little bit of extra hair. So it doesn't have an Euler product. It doesn't have sort of some obvious kind of bound on the small Dirichlet coefficients. So in fact, we actually have to invoke this result to bound the small coefficients. But nevertheless, you can kind of do a lot of these kind of standard analytic games you want to with this sort of function. Kind of extract this sort of bound from it, provided that x is pretty big. And again, in kind of the index sort of subfield world, this kind of handles those f with disk f divided by capital X, basically the 1. So we've sort of gotten down to a little bit more than 1/3, and kind of below sort of 1/5. Those are good, but kind of between those two things, we're going to need to do more. So what is the more we're going to do? Well, the Shintani zeta function.
Shintani do it over Q.
Sorry?
The Shintani zeta function, he defined, or maybe Sado, did Shintani just define it over Q? I know they, is that what does, that's.
I believe Shintani himself only defined things over Q, as I believe sort of Sato. Not absolutely certain on that. Certainly, kind of a lot of the analytic properties of this, particularly like the functional equation and things like that, were first worked out by Transposition and Wright, again over a global field. But as to what Shintani himself did, I'm not totally sure.
And the Archimedean fact that is a weird double gamma function, if I'm not mistaken. Again, it's a function of order 2. It's not, maybe
I'm pretty sure it's an entire function of order 1.
just ordering gamma function.
I believe so. Yeah, so
I mean, what it's very good for is to show that when you have a pole, which you can recognize that the error term can't be smaller than something. Because you, as you said, you smooth. The analytical conjugation is infinite smoothing. So any pole that's off the line, and they do recognize the pole.
yes, absolutely. But yeah, no, I mean, so I think so Shintani proves that this is an entire function of order 1 over Q. And I believe it's in Wright's thesis where he kind of does this over a number field.
And maybe real quick, maybe you can indicate, should we think of this analysis as being something like apply Poisson summation and then apply a trivial bound? Is that kind of a model for?
Yeah, so I think that's like a kind of reasonable interpretation. I mean, really what I'm doing is basically applying a convexity bound for an L function. It's like a little bit of a weird convexity bound because again, like we don't have Euler product, we don't have Ramanujan. Things are like a little bit skewed by our uniform understanding of the small coefficients, but essentially that's kind of what we're doing. All right. So we need to do something kind of to get between kind of this sort of trivial bound and this sort of asymptotic bound that works eventually, but it leaves a pretty wide range of things where we need something. So what's true is when you look at the Shintani zeta function, if you look at kind of any of these geometry of numbers estimates, these sort of parameterizations always kind of overcount things. The Shintani zeta function, so one of the tools available to kind of count arithmetic objects, actually counts cubic rings, not just cubic fields, which you can basically sort of think of as being kind of corresponding to maximal cubic rings. There's kind of a built-in overcount sort of in this sort of problem, and kind of the kind of standard sort of arithmetic statistics kind of talk with and say, well, okay, great, now we just do some sieving, kind of throw that out. Here we're actually going to exploit that overcount. So, in particular, suppose L over F is a cubic extension. It's smaller than the range where you kind of know how to start counting things very well. With this L over F less than this sort of disk F cubed kind of threshold. What I want to do is I want to consider how many rings there are inside this one cubic extension, and if they come up to this sort of point where I actually start getting a basically perfect value.
Robert, the zeta function also counts Q times quadratic fields, right? And that, don't you have to deal with that?
Because we're going for an upper bound here, we don't.
Then we don't care.
It's like there's a whole lot that's really nice about the fact that we're not shooting for precise asymptotic. At basically any step.
For the main term, full field, you have to get it right.
Sure, for the main term for the small field, we have to get it right, but for us, luckily, Gatskovsky right got it right.
Yeah.
So,
I see.
all right. Well, how many sort of cubic rings do you expect to see inside L to kind of come up to this kind of perfect threshold? You should expect to see, well, sort of the discriminative of a cubic ring is going to differ from the discriminative of its sort of maximal sort of ring by square. So kind of naively, you should expect to see sort of big O this F cubed over this L, all those square rooted cubic rings side of L with discriminant up to this bigger threshold. And so just inside this one L, you should expect to see kind of this many sort of cubic rings. And sort of asymptotically, sort of if x were like really, really huge, this would sort of buy you absolutely nothing. But for us, x is really small. Everything is about paying attention to the powers of discriminants. And what does it end up giving you? Kind of a bound in the form epsilon plus epsilon, disk f to 3 halves plus epsilon in this range. And this will be sort of useful if x is, in this case, I guess, bigger than this f. And correspondingly, kind of in the sort of field story, which I've now erased, if this f is bounded by minus. All right. But all this is saying you should expect to see. And actually realizing that expectation is non-trivial. And in particular, we don't realize it kind of for any kind of field L by itself. To actually sort of capture this and kind of get kind of complete the proof of this basically this point-wise result. We actually kind of need to sort of explain a little bit of averaging. Averaging over L, I should emphasize here. And we end up sort of at the end of the day needing to invoke Ziegel's theorem to get this result, to realize this expectation. So I think this is sort of the most subtle part, at least of this kind of pointwise result.
Siegel has many things.
Great. So the sort of theorem of Ziegel I'm sort of referring to is essentially what this sort of boils down to. Once you kind of average over L, you're kind of essentially wanting to count sort of ideals inside sort of some extension of F with pretty small norm. And that feels like it should be an easy problem. But if you actually just want to sort of say you have a lot of ideals with very small norm, you need to know something about the residue of the appropriate zeta function. So we invoke Ziegel's theorem to give a lower bound on that residue to ensure that there are many such ideals. All right. And so this gives the pointwise result. And if you've sort of been paying really close attention to sort of, especially my sort of disk F sort of parts, we have now this little tiny gap where we're sort of stuck between, we know how to handle things that are bigger than epsilon 1/3 plus epsilon. And we know how to handle things smaller than epsilon 1/3 minus epsilon, but we don't quite have epsilon 1/3. And that's where this average result ends up being useful. So to do better on average, well, we need to improve some part of this argument on average. And what is the part where it feels like there's the most to gain? It's in this sort of first argument where you invoke the trivial bound on the relative class. Want to do better than trivial on sort of the relative class. And there's sort of a long history of kind of studying this problem without the relative part. And in particular, there's a philosophy that's kind of made kind of, I think, sort of very kind of clear and kind of nicely written out in work of Ellenberg and Venkatash that exploits split primes to get some cancellation or savings over the trivial bound for the full class. So of Ellenberg and Venkatash. It gives savings in full class group origin based on split primes. And unfortunately, that's not going to be good enough for us because we sort of really need the relative class group. Because in this approach, where I kind of factored out the class group of F at the start, we're sort of bounding that kind of as a constant on average, essentially. So we sort of have basically a perfect bound on the class group of F, which means I need to make sure that any savings I get comes from the relative class group. And unfortunately, this lemma doesn't quite give us that. So what we do is we improve a variant for relative class groups. It uses sort of a relative Arich-Halef class group, kind of defined as like the kernel of the norm between the two Arich-Halef class groups. Kind of is very much modeled on this group. And you would sort of get a kind of very sort of similar kind of saving if you can guarantee saving if you can guarantee many split primes. And in particular, sort of the range of the primes we're talking about are some sort of absolutely tiny powers of the discriminant here. So sort of no hope to get something sort of for every field. But what we do past that is we use discriminant uniform zero density estimates to ensure there are indeed sort of many split primes in most F. So in particular, sort of the so we sort of the actual discriminant uniform zero density estimate we invoke is due to myself and Jesse Thorner. There's also some follow-up work of Thorner with Asif Salman that would kind of also work here, and also work of all three of us that would work. But in particular, it's really important.
Can you just say which L function?
Yeah, for Ray class L functions. That's sort of how we invoke this.
Be more specific.
Okay. So,
I'm interested.
okay, absolutely. So there are kind of actually two steps at which we have to invoke the zero density estimate. So we did this sort of twice. First, for I guess I'll say zeta f, and to come up with sort of better notation here, but I'll say zeta f sub 2. And what this basically means is, well, again, we're actually structuring everything as an induction. And if you want, this is sort of a quadratic subfield. If I'm looking at the case of D4, this will be some quadratic field. This would be kind of 2 steps down from my top field. This would just be Q. So in this case, I'd just be looking at quadratic universally L functions over Q. But in general, it's some sort of quadratic Ray class L function over some number.
Zero density on near the line 1.
Near 1, yes. Okay.
Nothing uniform. I mean, so it's just very close to the line.
Very, very, very close to 1. Yep. I mean, I'm sort of most of the way done, which is good since I think I'm a little bit over time. But just to ensure there are many primes in F. Primes in F. Then again, in zeta k over zeta f, ensure you get many primes in F that split in k. right? So if you want to ensure that there are kind of many primes at slightly k, the first thing you need to do is make sure there are many primes available. Then you make sure that they do the right thing. And so we kind of do this twice, but it ends up kind of giving us then sort of this average result, which then sort of finally kind of catches the gap between these kind of sort of exponents x to the 1/3 minus epsilon and x to the 1/3 plus epsilon. So we kind of get that as far as we want. And then the rest of kind of the proof of the theorem is just kind of sweeping up the details. And there's like a little bit more to be done, especially when it appears you're getting the right logarithms. But essentially, kind of that's the hard part of the work. I think that's a great place to stop.
Seems quite a miracle. But to one third and just that you got over that little hump.
It was a miracle.
Is there some obvious reason why you got into that position? You know that?
Nope. I felt like when we came up with the idea to kind of use this sort of I felt like a very good idea. Then you kind of work through the numerology, you kind of get to exactly this x to the 1/3 minus epsilon, and you kind of have a bad
There's
day.
a gap.
Yeah.
Usually you go this side, that side, they don't close.
That's right, that's right.
Once it closes, one third.
I don't have a good answer to that, unfortunately. And I think, yeah, I don't have a good answer. I guess there's some sense in which I guess like maybe you can kind of predict sort of the exponent of kind of 1 plus epsilon that we sort of get pointwise by the fact that sort of S3 is kind of built out of kind of 2 abelian extensions, and maybe you can kind of imagine that as twice 1/2. And so maybe that could have been predictable, which then kind of see that, but no, I don't have a great answer beyond that.
Sorry, so step 3, you really needed to be bigger than x to the 1/3 minus epsilon.
I wanted sort of this subfield to be smaller than x to 1/3 minus epsilon.
For step 2.
For step,
Oh, sorry, I missed counting. Sorry, for step 4, you wanted it to be. Okay, my question was in the middle board where you write this
Yeah.
down on the.
But last week he was making the speaker read out every sentence he wrote. So.
It would not have been enough to know that for discriminant up to x to the epsilon.
So I guess I'm not sure sort of what that is, but what I'll say is like, yeah, so I think, so this is essentially sort of the best version. It's not quite enough. So I'm assuming that sort of little x, the sort of route of the discriminant is kind of bigger than sort of this gap. That's just kind of coming about from like just sort of some optimizing some sort of various choices of parameters. This sort of ends up being kind of fundamentally there. If I sort of got rid of this epsilon, I'd lose an epsilon in the uniformity bound, and losing an epsilon is everything.
I guess another way to ask the question is if you had a weaker estimate where the exponent of the discriminant were much bigger on the top right part of the middle boards.
So here,
If that were much bigger,
Oh, gosh.
it would fall apart.
yes.
Okay.
You said you used convexity, but
Yeah.
in the sort of discriminant aspect
Discriminant aspect, yeah.
of, I think, all some convexity, but I don't know why.
Yeah, and T aspect, at least sort of what I've seen is T aspect over Q. I expect probably it could work over a number field, but that's somebody else's work. I don't want to kind of speak to it. If
So
you,
it would be interesting to have such results.
I would-
in aspects.
absolutely, absolutely. Yes, and
The Shitani zeta function, which is so,
Mhm.
as he said, it's just Poisson sum applied.
That's right.
And the zero set is much more complicated, which is why
Mhm.
it's quite tricky. My experience, if you want to make things, like if you want to count the number of integers up to x, you say I use the Riemann zeta function.
Mhm.
That doesn't give you such a quick bound that you can see with your eyeball. So it's used, and that's exactly what I mean by using directly Poisson sum in the setting where you're using it. What this is very good for is to see the meromorphic continuation to the left, which you're much less interested in. And I would imagine that whatever you're doing is visible directly at the level of the lattice. So it's a similar thing to if you're counting lattice points in a ball in higher dimensions, you could form a FC zeta function, and then it becomes much less transparent as to what you're doing. So that's exactly what I was saying at the beginning. You see, when Davenport was doing this, he didn't use the full Poisson sum to look to the left. On the other hand, there's no question that the poles that you see from this, you wouldn't see any other way. And that it is very interesting that it's a zeta function in the sense of it's done inside of that. I think the miracle what you've done here, which is kind of remarkable, is that you made trivial bounds from either side, and then you were able to get to a point where you do something, it's really remarkable.
Yeah, so we felt very lucky. Again, like for a day, it felt very unlucky, but yeah, so I guess kind of regarding Poisson, that's sort of an interesting point, not something I've thought about. So I kind of don't want to kind of make any comments sort of directly toward that, but it's definitely something to be thinking about.
Could you explain again how you passed from all the fields of the Fermi-Galois group to just agree to assumptions of that?
Sure. So I guess like there was kind of one point sort of a place where I kind of had an approximately equals or something like that. Yeah, absolutely. So essentially what's going on there is we're going to kind of rewrite sort of this step. So we sort of have a sum over f, h, and some classic thing. This is kind of innocuous by induction. Then we sort of have k and sort of this fg of x with fk being equal to f. I think this is the piece you're asking about, is that right? Yeah, so essentially sort of what's happening here is where sort of this kind of like transposition is coming into play kind of at a moral level is you should sort of not expect kind of the ramified primes of this quadratic extension to have anything to do with each other. I'm going to just write down some random sort of quadratic extension like that. Probably it's going to have to kind of have some prime in which it kind of has sort of it's ramified in kind of one place and kind of not in any of the conjugate places. That would kind of give you sort of this Galois group would give you a transposition, which is enough to actually ensure that the full Galois group is this group G. So what's sort of left to do is to understand those things that are give you a smaller Galois. And to do that, we actually come back to our sort of main technical result, the sort of uniformity bound. And it actually sort of applies to those extensions as well. So we're going to assume that sort of this field F is very, very small. And then more or less, you should kind of think that we can handle these sort of exceptional Galois groups that might arise as quadratic extensions using kind of analogous tools. So in fact, we actually invoke a zero density estimate again, kind of to handle sort of those things. So there is a little bit hiding here. But again, sort of morally what's happening is, I'm just trying to say that kind of generic quadratic extensions should give you Galois group G. And so corresponding, I can understand things with Galois group G by understanding generic quadratic extensions.
Any questions from Zoom?
There are no more questions here or on Zoom. Let's have the second time.